morning everybody. Hope you're all healthy and safe at home. We are moving to the next session of our second module, section 9.13, surface integrals. So the surface integrals can be related to the concept of the arc length, which we have done in case of 1 dimension, 2 dimension and all. That is, if we are given any function, say y is equal to f of x, then the arc length, if you guys remember, the formula was arc length is denoted by s, small letter s, and it was equal to integral a to b root of 1 plus dy by dx whole square into dx. Okay, so that is the concept of arc length of any curve or of the graph of any function, say y is equal to f of x. Now we are moving on to the same concept, what will happen in the case of 3 dimension. That is what we are going to discuss. We are introducing the concept of surface area. Instead of related to arc length, we'll have the surface area. You will understand the relation once you come across the formula to calculate the surface area. So first what we do is, again, we are given any surface. You can see in the figure there is a surface S, okay, and that is projected in the XYZ plane. So we are given a surface. What we do is, we'll consider the corresponding region D, you can see, in the XY plane. Okay, and as usual, like we have partitioned the intervals and partitioned the region, here also again using parallel lines which are parallel to x-axis and y-axis, we shall partition this region into sub-regions. Okay, and we will take a portion, say dk or something, and we will project it to the surface. Okay, I hope the concept is clear. We are partitioning this into many sub-regions, and we will take any particular sub-region and project it to the surface. So here in this case, once we are projecting this region onto the surface, we can form two quantities. One will be the portion SK of the surface, that you can see one a dark shaded gray, you can see an ash color which is curved a bit. That will be our SK, and corresponding to this SK, related to the tangents passing through this surface, we can form a tangent plane also. Okay, so corresponding, because this is the difference which happens in the 3 dimension case. So when we have XYZ plane, when we are projecting this surface, projecting this sub-region to the surface, we get two portions. One will be SK, which is related to the surface itself, and the other will be denoted by TK, which will be the tangent plane, which you can see the perfect rectangle shape over here, that will be TK, and the SK will be the one which is a bit curved. Now with the help of this TK and the notation, we can easily formulate the formula for the surface area, which we shall see later on. Now in this lecture, I'll just give you the formula for the surface area. So that is, if f be a function for which the first partial derivatives fx and fy are continuous on a closed region R. So just remember, the partial derivatives must exist and they must be continuous on the region which is considered on the xy plane. Then the area of the surface over R is given by, it is here also, it is there is an S coming in, so the notation is A of S, which is equal to double integral over R root of 1 plus fx of x comma y whole square plus fy of x comma y whole square into d. So I hope you can guys relate it with the arc length that we had stated in the beginning of this lecture. That was, it was nothing but 1 plus dy by dx whole square into dx. So here we have two variables, so we have to consider the partial derivatives, and we'll have two terms, fx whole square plus fy square into dA. So this is the formula for the surface area, and we have discussed the geometrical interpretation also, and the how to derive this formula we shall discuss about that in the later classes. So with this, we shall wind up today's session. Thank you. Stay home and stay safe.